Hi, and welcome back to the second lecture of three on chapter three. Today, what I'd like to do is to use the equations that we came up with last time to try to arrive at what are called equations of motion. Now, equations of motion describe the position, the velocity, and potentially the acceleration of an object at any given time. Now, if you remember last lecture, I had mentioned that I was going to start with some simplifications. We're going to make some simple assumptions about things. And then as the class goes on, we're going to add levels of detail. The assumptions that we made last time were that our objects are points that simply have labels attached to them, so they don't have any internal structure. We also made some assumptions, about one-dimensional motion. Today, the assumption that we're going to make is that all of our accelerations are constant. Now, we'll relax this condition later on, but by assuming an acceleration that's constant, at least right now, what that's going to enable us to do is to start to build up a foundation. And as the class goes on, we'll relax the condition on constant acceleration and help make that foundation even more solid. So, that said, let me remind you about the equations that we came up with last time. The first thing we came up with was an equation for displacement. It looked like this: your final position minus your initial position. We also came up with an equation for something called average velocity, which was how your displacement looked over time, how your position changes with respect to time. Now, if I expand this out using our notation that we used last time, it looks like this: xf minus x naught over tf minus t naught. Next, we came up with an equation for average acceleration, which looked like how your velocity changed with respect to time. Your velocity is vf minus, or your change in velocity rather, is vf minus v naught, and your change in time is tf minus t naught. Now, we're going to make some assumptions to make our life easy. The first assumption that we're going to do is to assume that we're using a stopwatch, which means that all of our initial times are zero. We're always free to take and reset the stopwatch to zero and then just let the counter run. So, T naught is zero right here. The next thing we're going to do is to reindex things. Now, it's understood that x naught, t naught, and v naught refer to things that happen initially. At the very beginning, your position is this. At the very beginning, your time read that. At the very beginning, your velocity was this. What I'd like to do is to reindex xf, tf, and vf. It's understood that these are final quantities. This is your position at the end of the day. This is your time whenever you hit stop on the stopwatch. And this is your velocity whenever you look at what your velocity is whenever you stop your stopwatch. So it's understood that that's the case. So what I'm going to do is to call this just x, t, and v. So in the future, when you see x, it should be understood that we're talking about the position at a given time. When you see v by itself in the future, it should be understood that we're talking about your velocity at a given time. Now, the final thing we're going to assume is that our accelerations for right now are constant, like I had mentioned earlier. Now, when you do that, what that means is that your average, that is what your acceleration is, we'll say, between point A and point B, is the same thing as your instantaneous. That's because it's constant. So what we're going to do is to every place that we see a average, we're just going to call it a for right now. That's a true statement because our acceleration is constant. So when you do that and you reindex things and you put in the fact that your initial time is 0, you end up with the following equations. Displacement is x minus x naught. Your average velocity is x minus x naught over t. And your acceleration is v minus v naught over t. Now, what I'd like to do is to take these three equations and apply them to a thought experiment, a simple problem that's a little more abstract than what we're used to. So let me draw a coordinate system and I'll talk you through it. This is y, this is x. Now, imagine a car that sits, we'll say, right about here. It has an initial position of x naught. Now, it's also, we'll say, moving to the right. It has an initial velocity of v naught. Let's assume that it accelerates in this direction as it goes further and further and further and further to the right and goes faster and faster and faster. At some point, at some time t in the future, when it gets to this point in space, which we would like to predict the location of, x, it has a velocity v. What we would like to do is to find both x and v at a future time. That's the goal. Now, our equations are right here. We would like to find the equations of motion. Now, we're not going to worry about an equation that explicitly gives us acceleration because our acceleration is constant and we can always solve for it. However, we do need equations for v and for t, rather for x and for v, that give us positions and velocities at some later date. Now, so that said, what I'd like to do is to start with this equation right here. Your acceleration, which again is constant, is v minus v naught over t. Now, we're going to assume for right now that we know our initial velocity, and we're also going to assume that we know our initial position, and we also know the acceleration. Now, if you look at this equation and you do a little bit of algebra on it, you have v minus v naught is equal to a times t. If you solve for v, you have v naught plus a times t. Now, this right here will give you your velocity at a future time if you know your acceleration and your initial velocity. So this is one of the equations of motion that we're looking for. We actually call this the kinematic equation. And I'm going to number this one as the first one. This is the first kinematic equation right here. So, here's what we have so far. The first kinematic equation says that your velocity at some point in the future is equal to whatever your velocity is now plus a times t. Now, the next thing I'd like to do is to find the position at some future time. If we go back over here and look, this equation doesn't do us a whole lot of good, even though it does have position in it. It's sort of an open-ended equation. It'll tell you displacement if you know your final position and your initial position. But we're trying to find this, and we don't know enough information for this to be useful. This is the only other equation that I'm aware of that has a position in it. So let's write this over here. Now, I'd like to stress that this is the average velocity. And average means exactly that. When you take an average, what you do is you add up everything. And then you divide it by the number of things that you have. Now, if you remember when we came up with these equations right here for averages, they only depend upon your initial position and your final position, your initial velocity or your final velocity, stuff that you know at the beginning and stuff that you know at the end. So here, if you were to take the average of your velocity, you only have two velocities that you can work with, v naught and v. So another way of thinking about your average velocity is what you get when you take and you add up the velocities that you have and you divide by the number of them that you have. V naught plus V divided by 2. This is fully equivalent, which means that you could take and you could rewrite this the following way. So I'm going to multiply both sides by t and then move the x naught over to the right-hand side. Now, what I'd like to point out is this. This is something that we would know or we would perhaps be able to figure out at the very beginning. This is your initial position. This is the point in time that we're interested in when it comes to finding out what position is. This, again, is information that we would know at the very beginning of the problem, your initial velocity. This, however, is your velocity at this time. Now, we don't know this, but we can find this from the first kinematic equation. If you remember, the first kinematic equation said this. Now, what I propose is we take and we put that V into there, right there. So I'd like to pull the half out, at least temporarily. So let me do that as an intermediate step. T over 2. This is V plus V naught. And let me put the this right here now into this point right here. That is x is equal to x naught plus T over 2 times V naught plus AT plus V naught. Now, if I allow this V naught and this V naught to group up, I have T over 2 times AT plus 2V naught. Now, let me go ahead and multiply the T over 2 through. When you do that, you get x is equal to x naught plus 1/2 AT squared plus V naught. This right here is the second kinematic equation. So, we have two kinematic equations so far. What I'd like to do is to get a third kinematic equation that helps us eliminate time. So, let me do that. Our kinematic equations so far are let me scroll up here a little bit. I guess not. We have so far V is equal to V naught plus A times T. X is equal to X naught plus 1/2 AT squared plus V naught T. What I'd like to do is to take this equation and solve it for time and then plug what I get into the times that I see right here. So let's work with that. V is equal to V naught plus AT. AT is equal to V minus V naught. T is equal to V minus V naught over A. Now, every place I see a T in this equation, I'd like to plug this in. So X is equal to X naught plus 1/2 AT squared plus V naught T, or 1/2 A V minus V naught over A squared plus V naught times V minus V naught over A. Now, the next thing I'd like to do is to move the X naught over to the left-hand side just to make life a little bit easier. So X minus X naught is equal to 1/2 A times V minus V naught over A squared plus V naught times V minus V naught over A. Now, I'd like to point out that the square makes this A squared in the denominator. If I pull it out over here, it makes this 1 over A out in front. There's also a 1 over A out in front over here as well. So if I multiply both sides through by A, it should eliminate the A's that I see on the right-hand side, and in turn, it'll put an A out in front on the left-hand side. Now, the next thing I'm going to do is to the right-hand side, go ahead and use FOIL on this square right here. 1/2 times V squared minus 2V naught plus V naught squared. On the right-hand side, I'd like to continue multiplying things through. I want to take this V naught and multiply it through as well. So I have a V naught V minus V naught squared. Now, left-hand side, A, X minus X naught. That hasn't changed. Okay, so now if you take a look here and multiply this 1/2 through on the right-hand side, you have a 1/2 V squared minus V naught plus 1/2 V naught squared plus V naught V minus V naught squared. Now, watch what happens. This right here is going to cancel with this. You have a plus 1/2 V naught squared minus V naught squared, and what that does is to combine to give you a minus 1/2 V naught squared. So at the end of the day, you have A times X minus X naught is equal to 1/2 V squared minus 1/2 V naught squared. Now I'm going to multiply both sides by 2 and switch sides. And when I do that, I get V squared minus V naught squared is equal to 2 times A times X minus X naught. Now, sometimes you might see this also written as 2 times A times delta X, because this is in fact the same thing as delta X. So what you have here is a third kinematic equation that relates the velocities to things to their accelerations and their displacement. Now, 3 kinematic equations, and with these 3 equations, we can actually do quite a bit of stuff. So that said, what I'd like to do next is to take a look at a few problems that just deal with constant acceleration in its many and various forms. So, next up, and also I'd like to I'm going to work these as word problems, because what we need to start developing is a framework to attack these things. So, here's what I have. Here's an example. A car, initially at rest, accelerates to 75 miles per hour 10 seconds. Find the position of the car and the average acceleration. So here's a word problem. So let's start talking about plans of attack. So the first thing you should do after you read your word problem is to draw a picture. When you draw pictures, what that does is to allow you to draw a coordinate system. And as I mentioned, before, when you have a coordinate system in place, that means that you can actually start to invoke mathematics. So here's our coordinate system right here. To make my life easy, since I can move coordinate systems around however I want, what I'm going to do is to have the car start here at the origin. That means my initial position is going to be 0. That's fine. Now, we know our initial velocity is equal to 0. By putting my coordinate system here, I've also managed to make my initial position equal to 0. So, I'm going to say it's going to move to the right. At some point over here, we're not sure where, that's one of the things we have to find. Our car is moving to the right with a velocity of 75 miles per hour. Now, we know we're going to have to convert that to meters per second, but we'll deal with that here in a moment. Now, I know that's going to happen 10 seconds after it starts to move. So here's my car right here. Now, the next question I should ask is, how would I have to push this car in order to make it do this? Well, the acceleration I would expect to be in this direction. This is the direction I would have to push it in order to make it do what it's going to do. So here's what I've been given. From what I've read here, I have an initial velocity of 0. I've set things up so my initial position is 0 as well to make my life easy. I have a final velocity of 75 miles per hour, which we're going to have to convert. I also know that that's going to happen at 10 seconds. Now, what I would like to find, according to my problem, is x and also a. The next step we need to take is to convert this velocity into something that's a little bit easier to handle. So we know 75 miles per hour. To convert that, and let me get my little conversion sheet here. Let's see. We know that there are 0.447 meters per second for every 1 mile per hour. So when you do that conversion, and let me do it. You get 33.525 meters per second. Now, again, I want to stress that we round at the end. And if you take a look here, we have 2 sig figs here, and we have 1 sig fig here. So at the end of the day, when we find our position and we find our acceleration, we're going to round those to 1 significant digit. Okay, so the next thing I do is to write down the equations that I know that describe motion. Since we're dealing with constant acceleration, we have 3. We have v is equal to v naught plus a times t. We have x is equal to x naught plus 1/2 at squared plus v naught t. We also have v squared minus v naught squared is equal to 2 times a times x minus x naught. So, once we've written our equations down, we should look at the stuff that we've been given and decide on what we can eliminate to make our life easy. For example, I see that my initial position is 0. I also see that my initial velocity is 0. So every time I see a v naught, I should be able to cancel that out. Every time I see an x naught, I should be able to cancel that out as well. So what that does is to take these three equations right here and simplify them. V is equal to a times t. X is equal to 1/2 a times t squared. And v squared is equal to 2 times a times x. Now, the next thing you need to decide is, what can I solve for? If you have enough information, perhaps you can solve for a. If you have enough information, perhaps you can solve for x. But unfortunately, from what I see here, if I want position, I need to know what my acceleration is. Now, thankfully, though, if I look at this equation right here, I know that after 10 seconds, my velocity is 33.525 meters per second. So I can use this equation right here to find acceleration. So the first thing I'm going to try to do is to find acceleration using this right here. And I solve for a, it's v over t. So v, once again, is 33.525 meters per second. T is 10 seconds. So my acceleration is 3.3525 meters per second squared. Now I want to stress, do not round this number yet. You want to wait until the end of the problem to round things, because we're going to need to use this acceleration whenever we try to find the position. Now that said, we have options for finding the position. We can use this right here, and we can use this right here. Which one you use doesn't matter. It's entirely fine either way. I'm going to use this one right here. X is equal to 1/2 at squared, or 1/2 times 3.3525 meters per second squared times 10 seconds squared. Now, before we do this calculation, I'd like to point out that this right here is the most common mistake that I see, dropping the square on this. Make sure that you square this. So, when you actually do this, let me get my calculator and I'll do it. A half times 3.3525 times 10 squared. $167.625 meters. Now, when we're done with our calculation, we're going to write down the answer. The acceleration here is 3.3525 meters per second squared. But look, one significant digit is the least number of sig figs that we can have. That makes this 3. 3 meters per second squared. Our position x, 167.625. One sig fig, though, makes this 200 meters. Once you have your answer, you box it, and this right here is what would be graded. So, let's do another example. A rocket has an initial velocity, that looks bad. Let's get rid of that. has an initial velocity of 1,500 meters per second. If it decelerates to 750 meters per second over a distance of 2.5 times 10 to the 5th meters, what acceleration did it experience? And how long did it take? So, once again, the first thing you want to do is to draw your coordinate system. If you choose your coordinates wisely, you put your rocket ship at the origin. Now, its initial position is 0, but the initial velocity is 1,500 meters per second. It's going to coast this way as it slows down. That's what decelerate means. It means that you're accelerating in such a way to slow something down. And if you wanted to slow the rocket down, you would want to push on it this way. So the initial velocity is this way, but the acceleration is this way. Now, at some point over here, (2.5 times 10 to the 5th meters away), your rocket ship is still traveling to the right. It has a velocity of 750 meters per second, but it's slowed down quite a bit. What we would like to find is this distance right here. Actually, not the distance, sorry. But what we would like to find is the acceleration and how long this took. So what are we given? Your initial velocity is 1,500 meters per second. Your final velocity is 750 meters per second. You cover 2.5 times 10 to the 5th meters, starting at the origin. We would like to find A and T. Now, as before, you write down your 3 equations of motion. There's the first one, the second one, and the third one. Next, you take a look and see what simplifies. Well, unfortunately, not a whole lot. X naught goes away, and that's about it, which means that this equation simplifies to 1/2 AT squared plus V naught T. This right here simplifies to just X, since delta X is X minus X naught. Now, so acceleration, time, which one do we find first? Well, this has a time in it, and this has a time in it as well. But if you notice, both of them depend upon us knowing the acceleration. If I look at this equation, though, it depends upon the initial velocity, the final velocity right here, and also your position at the end of the day. It looks like we have enough information to use this particular equation to find A. So we have V squared minus v naught squared is equal to 2 times a times x. And if I solve for a, I have this. Now, all I need to do now is to plug stuff in. V is 750 meters per second squared. V naught is 1500 meters per second squared. X is 2.5 times 10 to the 5th meters. Now, if I plug this into my calculator, let's see what we get. That's 750 squared minus 1500 squared divided by 2 times 2.5 times 10 to the 5th power. Let's see here. Minus 3.375 meters per second squared. Now, just for reference, if you think about how the Earth pulls you down and how you feel here, this would be about the same acceleration that you would feel on Mars. About a third, it turns out, of what you would feel here on the Earth. So, as people in this rocket ship slow down, they feel like they're being pulled this way. And you'll also notice that it's negative, which is what we had anticipated when we did our problem over here when we drew it. Now, remember, we don't round until the very end. So the next thing I want to do is to find time. I could use this equation right here to find time, but that's going to involve solving a quadratic equation and then deciding on what makes physical sense. On the other hand, this right here has a t to the 1st power. And now that we know what acceleration is, we know our initial and our final velocities, we should be able to use it to find time. So, if I manipulate it a little bit, that's what I have for time. So let's plug some things in. Our initial velocity, final velocity, let's see. We have 750 meters per second for our final, 1500 meters per second for our initial, and our acceleration we just found to be minus 3.375 meters per second squared. Put this in your calculator. 750 minus 100 or 15,000 or 1500 rather. Divide that by minus 3.375. And you get (222) repeating seconds. Now, if I take a look at my problem here, I see 2 sig figs here, I see 2 sig figs here, I see 2 sig figs here, which means at the end of the day, we're going to round these to 2 significant digits. Our acceleration, which is one of the things that we're looking for when you round to 2 sig figs, ends up being minus 3.4 meters per second squared. And our time, when you round to 2 significant digits, is 220 seconds. Box your final answer, and there you go. Okay, let's do another example. In this one, I want you to imagine a car driving down the road, and the driver slams on the brakes. So, a car traveling with an initial velocity of 40 meters per second, skids to rest in let's see, if the car experiences an acceleration of minus 6 meters per second squared, how far did it skid? Okay, so once again, draw a coordinate system. We're going to put our car at the origin again, just to make our life easy. Our car is going to come to rest somewhere over here, so we know our initial position is 0. Our final position is unknown. That's what we're trying to find. But we do know that as it slows down to rest, as it slows down to a final velocity of 0 meters per second, that the acceleration is to the left, and it has a value of 6 meters per second squared. We also know that our initial velocity of our car set is to the right, 40 meters per second. So what we've been given here is an initial velocity of 40 meters per second, a final velocity of 0, an acceleration to the left of 6 meters per second squared, and an initial position of 0. What I'd like to find in this particular case is just how far it skidded. We'll write displacement. The next thing you do is to write your equations down and then simplify based on the information that we know. So I have that V is equal to V naught plus A times T. I have that X is equal to X naught plus 1/2 AT squared plus V naught T. I also have that V squared minus V naught squared is equal to 2 times A times delta X, or X minus X naught. We'll go ahead and write it that way. Now, given the information that I have here, this goes away, this goes away, this goes away, and this goes away. So if I rewrite these equations, I have V naught plus AT is equal to 0. I have X is equal to 1/2 AT squared plus V naught T. And I'll also have minus V naught squared is equal to 2 times A times X. Now, we're trying to find delta X, but if you think about it, delta X is X minus X naught, and our initial position was 0. So this is just the same thing as X in this case. So we're trying to find X. Now we have two equations that can give that to us. We have this one right here, and we have this one right here. If we wanted to use this one, we would need to find time. Now we can find time using this equation, but I recommend that we use this equation right here because we know our initial velocity and we know our acceleration. So if you take and write that equation over here, and then solve for X. Plug in your numbers. Let's whip out the calculator here. Now, when I do this calculation, I get 133 with 3's repeating. Now, I'd like to point out the following. This cancels with this, giving us a positive x. And it should make sense that as we move to the right and stop, we're going to be a positive displacement. Now, that said, let's take a look at the sig figs. I see one here, and I see one right here, which means at the end of the day, when we round our displacement, we're going to round it to one sig fig. And if you do that, our position, which is the same thing as our displacement in this case, is 100. Now, we're going to work one more problem, and this is a simultaneous problem. It deals with the motion of two things and trying to find when they start to pass each other, basically. It's a pretty useful problem to do to show you how equations can be coupled. Now, in this particular problem, I want you to imagine two cars. Two cars. I'm not very creative, so we'll call it car 1 and car 2. Are going to pass each other. Now, car 1 is traveling at a constant velocity. Got an extra thing there. Velocity of, let's see, 40 meters per second. Car 2 sits at rest at the origin. Now, when car 1 passes car 2, car 2 begins to accelerate. Now, it's going to accelerate at 2.0 meters per second squared. What I'd like to find is the following. When do the cars pass? And where? Okay, so let's draw our coordinate system. Now, here's car 2 right here. It's the one that's at rest. Now, to differentiate between it and car 1, since it's car 2, its initial velocity is 0. Now, here comes car 1. Moving this way. Car 1's initial velocity is 40 meters per second. When they cross, that's when car 2 starts to accelerate. Now, car 2's acceleration, which I'll call A2, is going to be to the right because it has to accelerate to the right in order to catch up with car 1. And it's 2.0 meters per second squared. Now, they go faster and faster and faster and faster. At some point, car 2 is going to hit the same speed as car 1, and they'll start to approach, and then it'll pass. Now, at this point right here, which I'm going to call x because we're trying to find it, we expect that to happen at time t, which we don't know. We're trying to find these two things. So, what are we given so far? We're given that car 1's initial velocity is 40 meters per second to the right. We're given that car 2's initial velocity is 0. We're also given that car 2 experiences an acceleration of 2.0 meters per second squared. Now, car 1 is coasting. It does not have an acceleration. Its velocity is constant. Remember, acceleration is how your velocity changes over time. So if there is no change in your velocity, then your acceleration stays constant. Or your acceleration, rather, is 0. So, no acceleration. What are we trying to find? Well, we want to find the point in which they have the same position, because we know at that point the cars are going to start to pass each other. So we need to find x, and we'd also like to find out whenever that happens. So at this point, what you do is you write down your equations, but you write down your equations, one set for car 1 and one set for car 2. So for car 1, we have v is equal to v naught plus at, but we're going to put 1s there to show that that belongs to car 1. Likewise, we have x1 is equal to x1 naught plus 1/2 a1t squared plus v naught 1, or v1 naught rather, times t. We also know that v1 squared minus v1 naught squared is equal to 2 times a1 times x1 minus x naught 1. Now, for car 2, we have v2 is equal to v2 naught plus a2 times t. We also have that x2 is equal to x2 naught plus 1/2 a2 times t squared plus v2 naught times t. Finally, we have v2 squared minus v2 naught squared is equal to 2 times a2 times x2 minus x2 naught. Now, that's a whole lot of writing, but hopefully when we take and we plug in some simplifications here, things will get a little bit easier. And sure enough, let's look at the acceleration for car number 1. Now, it's coasting at a constant velocity. That means that the acceleration is 0, and that means that all of this stuff right here goes away. So these equations right here are actually going to simplify. The first equation tells us that our velocity at any given time in the future is the same as the velocity that we started with, which should make sense. That's all it tells us. This tells us that the magnitude of our velocities doesn't change. That's fine as well. They're not meaningful to us other than to tell us stuff that we already know. What's really meaningful to us in this one right here is this equation right here. This says that the position of car 1 only depends upon how fast it's going and how long it's doing it. Now, let's look at what's going on with car 2. The important thing about car 2 is that its initial velocity is 0, which means that goes away. We can also get rid of this right here, and we can also get rid of this right here. So these three equations become a little bit easier. V2 is equal to A2 times T. X2 is equal to, oh yes, X2 naught, which I forgot to mention or write down over here, that's also 0 as well, isn't it? X2 is equal to 1/2 A2 times T squared. And then finally, we have V2 squared is equal to 2 times A sub 2 times X2. Now, we want to find when the cars pass each other, and also where they do that. When they pass, their positions are going to be the same. Okay? Now, this equation right here gives me the position of car 1. This equation right here, and also this one as well, gives us the position of car 2. I propose that we use this one right here. When you set them equal to each other, that is, x1 is equal to x2, v1 naught times t is equal to 1/2 a2 t squared. The first thing you'll notice is that you have a time on the left-hand side and a time on the right-hand side. Now, before we cancel out one of those times, what I'd like to point out is the following. There is a time at which the cars are in the same position. Remember, as the problem says, when car number 1 passes car number 2 at the origin, car number 2 is going to start to accelerate. So at time t is equal to 0, these sides are equal to each other. But that's a nonsense answer. We already know that. So we don't care about that being a solution. So it's obvious that when t is equal to 0, that's a solution, but that's not what we want. We don't care about that. So this will cancel out that right there. And whenever you take and I'll use a little bit of room over here. Let me get my eraser out. Let's see. Let me erase this right here just to make a little bit of space. That's the problem with these things. You don't have a lot of writing space. But that's okay. We can make do. So, that said, let's move that over there. We'll go ahead and have the t's cancel out. I get that v10, or v1 naught rather, is equal to 1/2 a sub 2 times t. So, if I solve for t here, I get 2 v1 naught over a2, which is 2 times 40 meters per second divided by 2.0 meters per second squared. Now, if you do the math here, 2 is going to cancel out this 2, which means that this is going to occur at 40 seconds into the future. So, when do the cars pass each other? Well, other than at the origin, 40 seconds down the line. Now, where is that position? Well, we have options. We could use this equation right there to find it. We could use this equation right here to find it. We could use this equation right here to find it. It really doesn't matter, okay? So what I propose is to use, we'll use this one right here because it looks pretty easy. So, x1, which is going to be the same thing incidentally as x2, is equal to v1 naught times t. Now, v1 naught is 40 meters per second. This is happening 40 seconds into the future. 4 times 4 is 16. You have 2 additional zeros there. 1,600 meters, or 1.6 kilometers approximately. Now, I want to remind you that if you look at the sig figs that we have here, we have 1 here, we have 2 here, and that's about it. So the least number of sig figs that we have is 1, and unfortunately we're going to have to round things to that. Now, conveniently enough, this is already rounded that way. This one right here, when we round it, is going to become 2,000 meters. So at the end of the day, when do the cars pass each other? Well, at 40 seconds. How far do they go? before they pass about 2,000 meters. Now, this ends lecture number 2 of 3 for chapter 3. In the next lecture, we're going to discuss free fall conditions and also what happens when you have an acceleration that isn't constant.